Okay guys, welcome to KTU lectures. In this video, we will be discussing some questions on performance analysis of pipeline and processors. Okay, most probably. So here some formulas you may not know and all of those situations can come. So through these questions, my basic ideology is that you will be learning when similar questions come, how can you do. So the thing is that you're going to learn with this question. I'm not going to tell you to do the question by yourself. It's just like we are going to learn by doing these questions. How you can approach such questions is what we are going to understand here. So first let us see the basic formula for calculating the execution time is instruction count into CPI into cycle time. Cycle time is actually can also be written as 1 divided by clock frequency. This much we have to know. Execution time is equal to instruction count into CPI into cycle time, and cycle time is 1 divided by clock frequency. Understood? So the first question is this. Sorry for the clarity issue here. So the first question is this. Here it says we have to calculate the execution time here. A processor execute 1.5 into 10 raised to 9 instruction with a CPI of 1.8 and a clock frequency of 3 GHz. It's clock frequency. Compute the execution time. So we know to calculate the execution time, it is, the formula is what? The formula to calculate, this was the formula that we have actually discussed in the previous slide. That is, calculating execution time is the total instruction. Right, we have to do the total instruction into CPI into clock frequency into clock time period it was. So we have said this was clock time period. We have said clock time period is nothing but 1 by frequency. So this question can be written as total instruction is given as 1.5 into 10 raised to 9 into CPI would be 1.8 into clock into 1 divided by 3 giga is what? 10 raised to 9. That you have to know. Giga is 10 raised to 9. Okay. So it is actually 1 divided by 3 into 10 raised to 9. Right. Is this 1 divided by 3 into 10 raised to 9. So this whole you have to solve. That is 1 divided by 3 into 10 raised to 9 is 0.333 into nanosecond. Nano means what? 10 raised to minus 9, right? Then you are going to multiply this whole and you are going to finally get an answer like you are going to just multiply it and get, you can write it in any unit. The unit, like you can write whether you get it in a nanosecond, you can write the answer in nanosecond, that is fine. Okay, so just you have to multiply it. That is only the basic funda behind this question. Okay, now let's understand this question. A program has 200 instructions. So if it's a non-pipeline processor, 5 stages and clock cycle is 1 nanosecond. And if it's a pipeline processor, we have 5 stages, clock cycle is 1 nanosecond and there is no stalls. We have to calculate the execution time of non-pipeline processor, execution time of pipeline processor, and the speed up. Speed up means the ratio of both of this. That's what speed up means. Okay. So first let us see how do we calculate the execution time of non-pipeline. We have total number of instructions into clock cycle into CPI is what we have to do. We all know that. So here if it's non-pipeline processor, how do we do that and how do we do it in pipeline processor are two different methods. So first you have to understand, as I told you, we have to discuss a basic funda here. See, you have to understand that if the number of stages are given for non-pipeline processor, if you consider here number of stages are given, so we know the formula. First let me write the formula. The total instruction we have no into CPI into clock cycle, right? This is the basic formula. So total instruction, we are doing the first part. Okay, that is the A part. Let us say total instruction we know it is 200 into CPI into clock cycle is 1 nanosecond. Fine, this much we have understood. The problem is CPI. What would be the CPI? For non-pipeline processor, the CPI would be the number of stages. So here if it's 5 stages, the CPI would be 5. So that would be the answer. Oh, sorry for guys. It goes a little back. These are my previous module 2 notes. Okay, 200 into the CPI would be what? 5 into 1 nanosecond we have to do. That means here if you see, for non-pipelined execution time, we know the total number of instruction into CPI into cycle time, and the CPI here is 5 for non-pipelined. So 200 into 5 into 1 nanosecond, we got the total execution time for non-pipeline processor. Okay, great. On that note, I wanted to talk about here. I want to talk about this B part. That is the B part. That is for that is for the execution time of pipeline processor. We have to know that if there is no stalls, it is given in the question. There is no stalls. No stalls means it's an ideal pipeline processor, because there is no stalls and no flashes here. So if it is no stalls, that means it's an ideal pipeline processor. So that means for ideal pipeline processor, the CPI value is 1. We know always 5 stages are there, but in case of pipeline processor, we have to understand that the CPI value would be 1 if there is no stalls. That is, here it's ideal because there is no stalls, and it's not talking about flash. So that means there will be no flashes. So that means the ideal CPI value would be equal to 1. So our calculation would be 200, the total number of instructions. In CPI is 1. It's gone again back. Okay. CPI is 1 into, sorry guys, I'm so sorry about this. Okay, it's 200 into time period is 1 nanosecond. So this we have to do. That is, if you see here, for ideal where there is no stalls, the CPI value here would be 1. So you get 200 into 1 into 1, that is 200 nanosecond. So how do we calculate speed up? See, now this is a speed up formula. You calculate speed up like this. Speed up is what? Non-pipeline time divided by pipeline time that you have to do. That is 5. This is a speed up time. So this is a formula for here. First non-pipeline, you calculate 200 into 5 into 1. Pipeline, you calculate 200 into 1 into 1. So speed up would be what? The division of non-pipeline divided by pipeline would give as our speed up. This much we have understood. Is that you have any doubt in this question, you can just say it in the comment section which question you have the doubt. First you have to specify the question number. This is question number 2 and the doubt in it. Okay, so I will just check that out. Okay, fine. Now let's see the third question. Here you have to understand a lot of new concepts you have to understand. So if you can't do it by yourself, it's fine. So there is a 5-stage pipeline processor which is executing 100 instructions, but there is a hazard. Load use hazard is using 15 stall cycles it is using. So clock cycle time is 200 nanoseconds. So compute the execution time. We have to compute the execution time. So it's not an ideal CPU. It's not an ideal pipeline processor because there is load use hazard is there, and each load use hazard would use 1 clock cycle, and here it is said there are 15 stall cycles used by this load use hazard. So how we are going to do? So you have to understand that CPI, what would happen here, you have to understand that is execution time would be, so the total number of instruction is 100 into CPI would change, okay, into clock cycle is 2 nanoseconds. Now what would be the CPI here? What would be the CPI here? If there is CPI, you can calculate like this. what would be the CPI here, how you can calculate is that if there is no using the cycles, if you have no load, then the total number of instruction is 100, each is occupying one cycle. So if there is no load, the total would be 100 cycles will be the, but here we are using what, here we are using load, so 15 cycles are also added with this 100, that is 115 is there. That means out of this you have understood, if there is this load use hazard, then 100 instruction each has one cycle and it is added with this 15. So total 100 plus 15, 115 cycles will be the initial condition was 100. If you divide this, you get what, 1.15. This is our effective CPI, that is a CPI in this case when additional 15 cycles are coming to this 100 cycles. We have to understand each instruction occupies 100 cycles. So effective CPI can be calculated in this way. See, effective CPI can be calculated like this. So 100 into 2 is 200. 200 into 1.15 we have to do. 200 into 1.15 if you do, what you will get, 230, right? So you get 230. That would be our answer. See how it is basically happening is that our basic formula is what, instruction, total number of instruction into CPI into clock time. Instruction is given to us as 200, CPI we have to calculate, and clock time is given as 2 nanosecond. Fine. Now CPI is something which you have to calculate. It's given that if there is initial condition, if there is 100 instruction, how many clock cycle will be there? 100 clock cycle only, initial condition. But what happened, 15 stall cycles are happening, so total 115 cycles would happen here. So if I divide 115, that is the current condition, with the condition where there is, that is where there is where there is no stalls, then you get 1.15. and if you multiply, so in the CPI space what would come, 1.15 would come. This is how you calculate the effective CPI. So 200 into 1.15 into 2 nanosecond would be our right answer. Understood how this question comes? If you have any question doubt in question number 3, you can write, specify the question number and the doubt. Okay. Now in this note, let's do the question number 4. A processor has this following instruction mix: ALU 50%, CPI is equal to 1, load 20%, CPI is equal to 2, store 10%, CPI is equal to 2, branch 20%, CPI is equal to 3. So the program execute this many number of instruction at 2 gigahertz, means this is the clock frequency. This is what the clock frequency is. How we are going to do? Here you have to calculate the effective CPI. How do we calculate the effective? 50% into 1 plus 20% into 2 plus 10% into 2. This is the CPI. This is 50% into 1, 20% 2, 10 into 2 plus 20% into 3, whole divided by 4, because there are 4 instructions. Not whole divided by 4, whole divided by addition of the CPI. I'm wrong in that. Sometimes it goes like this back, and I'm so sorry. Here their addition would give, how we are going to take the CPI average of all of this. Understood? So that means I will tell you 0.5 plus 0.4 plus 0.4 plus 0.6, you will get 1.9. okay, 1.9 you will get total. This part is not there. Okay, fine. So you get here when you are doing this, that is first 50% you have to convert into 0.5. that I hope you know. That into this 20% into 2, 20% again into 2, 20% again into 3, you get a sum as 1.9. So now you have this average CPI. Okay, so that you can put it in our. So now you have the total number of instruction is 5 into 10 raised to 6 is already given to us, into CPI value 1.9 you will write, and here this is given, clock frequency is given, so 1 by 2 into 10 raised to 9 you have to do. That would give us 0.5 nanosecond, that is 0.5 into 10 raised to minus 9. These all you multiply seconds, this all you multiply, you will get your final answer. Understood? So this was our question number 4. Now let's see question number 5. The pipeline processor has an ideal CPI of 1. We know that. Branch frequency is 20%, 14% of the branches are mispredicted, and the branch penalty is 3 cycles. Clock cycle time and instruction is given. So first, our ideal CPI is 1. But in the ideal CPI, some things are coming here. That is 20% of branch, 40% of branches are predicted, the branch penalty is the. So we know our basic equation. What is our basic equation? Let's start with the basic equation. That is a total number of instructions into the CPI into the clock cycle time, that is given 1.5 nanosecond. This n value is given as 1 million, that would be 10 raised to 6. This much we have understood. We have to calculate the CPI value. So CPI value would be ideal CPI value, that is 1, plus the problems here, 20% is what, 0.2 into 40% is 0.4 into how many cycles, 3 cycles. This would calculate the value that we needed, that is 0.08 into 3 you have to take, that is 0.24. So this would, that is, in order to calculate effective CPI, we are using this formula, ideal CPI plus branch fraction into misprediction rate into penalty. You will get this effective CPI value, that you are going to put it in here. Understood? In our basic equation. This I hope you have understood. Is there any doubt in this question? Please say it in the comment section. Okay. Now let's see the 6th question. Let's see the 6th question. In RISC-V pipeline, 30% of instructions are loads. 50% then we have 60%. This 50% of load causes 1 cycle stall, and clock cycle time is equal to 2 nanosecond. Program length is 2 into 10 raised to 6 instructions, and compute the execute time. Okay. This much things are there. So here 30% of instruction is load, 50% of load causes a 1 cycle stall. Clock basic instruction is the CPI's ideal value would be what? Ideal value would be 1. That you have to multiply it with 0.3 into 0.5 into 1 cycle stall, right? 0.3 into 0.5 into here 1 that you have to add it with the ideal CPI. This would give us the CPI that we needed. Okay, then in the basic equation, number of instructions 2 into 10 raised to 6, CPI you will get from here 1.15 into clock cycle time is 2 nanosecond. You have to just solve this. Understood? This is like the previous question itself. Fine. So I am dividing this performance questions in 2 parts. So here we have done 6 questions. In the next video we will do the next some questions also.